Hello classmates, we continue to study knowledge of three-phase AC circuit today. Last class we studied the triangle connection of the load in a three-phase AC circuit. In today's class we will focus on the power of a three-phase AC circuit. As we learned before, the load of a three-phase AC circuit can be either symmetric or asymmetric. Therefore, the calculation of power in a three-phase AC circuit mainly depends on whether the three phases of the circuit are symmetric. We will now discuss the power calculation of both three-phase symmetrical and asymmetric circuits. This will be analyzed from three aspects: actual power, wattless power, and apparent power. Let's begin by learning how to calculate the actual power of a three-phase load. The actual power of a three-phase AC circuit, that is, average power, is calculated by summing up the average power absorbed by each of the three phases. The expression for actual power is shown in Formula 451 for a symmetrical three-phase AC circuit. The expression for actual power is 3 times the phase voltage, multiplied by the phase current, and multiplied by cosine phi. For three-phase symmetrical load with star connection, while the voltage UL is equal to 3 times the root line voltage U up, the line current IL is equal to the phase current IP. Therefore, the expression of actual power is P equals root 3 times UL IL cosine phi. Similarly, for a three-phase symmetrical load with triangular connection, the wild voltage UL is equal to the phase voltage UP, and the line current IL is equal to the root 3 times IP. Therefore, the expression of actual power is P equals root 3 times UL IL cosine phi. It can be observed from the above formulas 453 and 454 that for a three-phase symmetrical circuit, the expression of actual power is independent of the load connection. However, the value of phi still depends on the impedance angle of the load, which determines the phase difference between the phase voltage and current. Next, let's learn about the calculation of reactive power for three-phase loads. It's determined by the sum of reactive power absorbed by the three-phase load. This can be expressed using Formula 455 in the case of a symmetrical three-phase AC circuit. The reactive power is equal to 3 times the phase voltage multiplied by the phase current and then multiplied by sine phi. This applies regardless of whether the load is connected in a star shape or a triangle. The expression of its reactive power. It can also be expressed as Q equals root 3 times UL IL sine phi. For a symmetrical three-phase circuit, the expression of reactive power is independent of the load connection. However, the phase difference between the phase voltage and phase current is determined by the impedance angle of the load. Next, let's study the knowledge related to apparent power of three-phase loads. It is emphasized that apparent power of three-phase circuit is not equal to the sum of the apparent powers of each phase, namely the total apparent power S. It's not equal to the apparent power of the U phase. SU plus the apparent power of the V phase, SU, plus the apparent power of the W phase, SW. If a three-phase AC circuit is a symmetrical three-phase AC circuit, then apparent power S is equal to the square of the active power of the three-phase load plus the square of reactive power, and then the square root is taken by calculation. It can be concluded that the apparent power S is equal to 3 times up multiplied by IP, which is also equal to the square root of 3 times UL multiplied by IL. Finally, let's learn power factor of three-phase load. Power factor of three-phase AC circuit. Cosine phi prime equals lambda equals to active power P and ratio to apparent power S. If the load is symmetrical, then the power factor lambda is equal to cosine phi. In the case of symmetry, cosine phi prime equals cosine phi is the power factor of a phase load. Phi prime equals phi is the impedance angle of the load. In a symmetric load, the power factors of each phase are different. Power factor value of three-phase load have no practical significance. In order to deepen the students' understanding and mastering the knowledge points of this lesson, let's look at an example. There is a symmetrical three-phase load with an impedance of each phase Z equals 80 at J60 ohm. The power supply phase voltage SUP equals 220 volts. We need to calculate the active and reactive power of the circuit. When the three-phase load is connected respectively into stars and triangles, solution 1, when the load is a star connection, the line voltage is equal to root 3 times the phase voltage. Line current is equal to phase current. Hence, UL equals root 3 times UP equals root 3 multiplied by 220 equals 380 volts. IL equals IP equals 2.2 amps. Cosine phi equals 0.6. Using the knowledge we have learned, active power and reactive power are respectively P equals root 3 times 380 times 2.2 times 0.8 equals 1.16 kilowatts. Q equals root 3 times 380 times 2.2 times 0.6 equals 0.87 kilowatts. Next, we will solve the second. When the load is connected in a triangle configuration, line voltage is equal to phase voltage, and line current equals to root 3 times the phase current. Hence, UL equals UP equals 220 volts. IL equals root 3 times IP equals 3.8 amps. According to what we have learned, active power and reactive power are respectively P equals root 3 times 220 times 3.8 times 0.8 equals 1.16 kilowatts. Q equals root 3 times 220 times 3.8 times 0.6 equals 0.87 kilowatt. This lesson is over. Goodbye.